Lydia asked me to record this, so we're going to go ahead and record. A couple of you have asked questions about Newton's method.
Yeah, like all of them.
I'm a little disappointed. We're not going to do all of them, so we can choose a couple that we can take a look at.
Question about part 2 on A, or
Okay.
how are we what are we solving?
You're talking about x equals the 50 of the cube root of 5. So the idea here is that I want a decimal approximation to the cube root of 5. I mean, the cube root of 5 is a good number and all, but if I want to know some decimal approximation for it, I need to come up with an equation equals 0 that I can use to solve for it. What equation suggests itself? But the problem with this equation is that it assumes that I have a value for the cube root of 5 to begin with. So that's not really going to help. I need a different equation that has a value I can actually compute in it. That would be an equal 0 equation.
One-third on.
So here we go. X cubed minus 5 equals 0. And this right here is a good candidate for using Newton's method. Yes?
Oh, okay, so like with these, you would solve it for 0 and then just call that after that?
Yeah, exactly. That's exactly it. So I've got an f equals 0 here. And now I'm going to, what's a good guess, starting guess here? Two works. Your starting guess should not be a hard thing. It should be an easy question.
Is there a chance that you wrote out the test page?
She took it on a different day. That is Amanda Richard.
Okay.
If you can just put it with her test and staple it, that'll help.
Okay. I only wondered if it wasn't good being a compliment.
Yeah. Yep. Okay, so we start off with an x0 equals 2. We've got an f prime, which is going to be 3x squared. And so now we can go through and start computing. Which is going to be x0 minus x cubed minus 5 over 3x0 squared. Sometimes people actually take and simplify this a little bit, because you notice that x cubed minus x squared is just x. So if you wanted to simplify it like this, then this would give you a nice computational formula. But this is not necessary. All of this right here would be optional. And it just makes it faster for your table to be generated. So if I use this particular formula, my x1 would be equal to 2/3 times 2 plus 5 over 12. And that gives me some decimal value. Four-thirds plus 5 over 12, giving us 1.75. And then I can now repeat that as many times as I need to until f of my value is 0.
You're using the x1 as a x0 for
Yes, that's exactly right. That's exactly right. That's the iteration idea. So x2 would then be 2/3 times 1.75 plus 5/3 1.75 squared. Just like that. And it just kind of keeps on going with that. second time, we get 1.7149, and so on and so forth. Does that help? What I would do if I were doing this on the calculator, if I didn't want to be fancy about it, is I would let y1 equal my function, x to the cube, x to the third minus 5, right? And then I would, on using trace and dy dx, I would get the values of f of x0 and f prime of x0. Write those in my table, and then do the computation on the main screen from there.
The number 3
Number 3 is going to take a lot of iterations, right? If you wanted to short circuit, let's see.
Like yesterday we did the store.
Yes, you want yeah. So with that, you could take something like store 2 to the x, and then what you're looking for is x minus, and now you can give the derivative by hand, right? So that would be x cubed minus 5 over 3x squared, and then store that in x also. And this now sets you up for iteration, because once you hit enter on this, if you hit enter again, it will iterate with the new value of x for you. Does that make sense? Okay, time for one more? Okay, what have you done with number 2?
I couldn't come up with the equation for the red dot versus the red dot.
So my hint to you was to add the linear motion to the rotational motion. So tell me about the linear motion.
Oh, it's going 5 inches in a second. 6 inches total.
Alright. That doesn't really tell me about the linear motion. I need a position equation. X of t equals what? 5t. There we go. So this is the linear part. What about the rotational part? Pretend for a moment that I just pick the robot up so that the wheel just spins. How would I describe the position of that red dot on the spinning wheel?
Maybe circumference. Something to do with that.
Something about circumference, that's right. How quickly is the circumference traveling? What's that? Pi r over t. Pi. Are you sure it's pi r over t? Isn't it 2 pi r over
I
t?
do.
Yeah.
So the radius is 1 here, so it's a pi.
Oh, I see. Over the period, okay. So that would give me the speed at which this is going. Do we know anything about the speed of the circumference relative to the speed of the robot? Hint. If the if the robot is going to travel at 5 centimeters per second, then the outside of the wheel has to travel at 5 centimeters per second also. So that means we actually have a number for this. This is 5 centimeters per second. And the radius, as you pointed out, is it 1 centimeter for the radius?
1 inch.
Or 1 inch? Either inch. Did I metricize this whole thing? I accidentally metricized this whole thing. I'll tell you, you put a guy in a physics class and you can't get out. Okay, based on that, I can figure out how long it takes for this thing to rotate around. Go ahead and find that amount of time. This is 5 inches per second. There we go. So I'm getting 1.26 seconds to travel one entire circumference. How does that help me figure out the rotational position in terms of time? Talk to me about the path that the red dot is following. What shape is that path? It's a circle. That's exactly right. And what do you know about circles? You actually know a lot about circles. If I draw myself a circle and put a point on that circle, then what can I say about the x and y coordinates on that circle?
It's circumference, obviously.
The circumference is distance around, but I'm looking for x and y coordinates here. And I can say something about that. I can say that x squared plus y squared is going to
there
be
any?
Yes, definitely. But I can say more than that. What if it were a unit circle? What would the x and y coordinates be? Cosine and sine, right? So if I now scale my circle to a radius of r, then the x and y coordinates are going to be times the radius, because I'm scaling it out. Oh, you mean we're supposed to actually use that stuff? Yep. So that on a circle, the x and y coordinates are always r cosine theta and r sine theta. Well, that's fine and all, but now, how do I express the angle theta in terms of t? It seems fairly clear that that angle theta is going to be continually changing as my time changes. And it's going to be changing at a constant speed. And the rate at which this thing changes is clearly equal to the, what's the total amount of angle around?
360.
2 pi, thank you, divided by the amount of time that it takes, which is the period. And we call that the omega, or the angular speed, is 2 pi radians divided by the period. Notice that the 2 pi radians divided by the period is the same as the speed of the object divided by the radius, just like that. And therefore, the angle that we will travel in any 1 second is equal to v over r times t. Now, that's measured kind of from an arbitrary 0 point here. So right at t equals 0, we're at the bottom, and these two are giving me slightly wrong expressions for it, because if I plug in t equals 0 here, let me do that. If I plug in t equals 0, then I actually get this point. And that's the wrong point on the circle. That's the wrong place in the circle. So what I'm going to need to do is to adjust this angle just a little bit so that I'm actually down at the bottom when t equals 0. So I can do that by subtracting pi over 2 from my angle to get me down at the bottom when t is equal to 2. So this gives me now my final expression for the x and the y, and the final expression is this guy right here. We've got 3 components to it. We have a radius, the radius of the circle, which pushes us out. We have a speed, and the angular speed that we are traveling at is in terms of v over r. And we have an initial starting position, and our initial starting position is literally negative pi over t. Just like that. Yes, sir?
I couldn't understand why the angle is omega t.
Oh, because the angle is changing at a constant rate as this thing travels around, just like that. Because it's changing at a constant rate, therefore, the amount of angle that you have is just rate times time. It's a linear function.
How would v over r?
Omega is v over r. If omega is v over r, then gosh darn it, omega is v over r.
Is v the velocity?
The speed that the robot is traveling. So in order for the robot to travel, the wheels have to actually keep up with it. And so they have to rotate at a rate of v over r. Okay? So to sum it up, notice that my starting location is expressed right here. So my starting location is at negative pi over 2, like that. Let's make sure I've got the correct direction of travel. If the robot is moving to the right, then are the wheels going to spin like this or like this? Are they going to spin clockwise or counterclockwise? They're going to spin clockwise, aren't they? And so that means that I actually need to make my time here go backwards with a negative sign like that in order to get the whole thing to go in the clockwise instead of counterclockwise direction. Way back in Trig Precalc, there's a whole section in the purple book on modeling circular motion. You guys did this. Does it not ring any bells?
Never did this. No.
Wow. Okay. Does it make sense? Because this is like a thing that you should be able to do. The omega is the hard part? Okay, yeah, so let's talk about the omega and make that as simple as possible. The key is that at a constant rotational rate, theta is just going to be omega times time. That's that full linear function idea. Okay? Now to get the omega, I just have to ask how quickly are angles changing as we go around. Okay? And the angle changes at a rate of 2 pi radians for every rotation. But the period of rotation we can figure as, because the velocity equals 2 pi r over period, we can figure the period of rotation as 2 pi r over the velocity. And so we get the angular speed is v over r. Or, if you've had physics and done rotational physics, you may remember that v is equal to r omega. And so if I divide both sides, omega is equal to v over r. And that makes life easy. Okay? So we have 3 components. We have our radius, which was easy enough. We have our omega, which is speed over r. And we have the starting angle, which is sometimes called phi, the phase angle. And then any circular motion is going to be modeled by cosine omega t plus the starting angle and sine of omega t plus the starting angle, and both of those multiplied by the radius. And that puts me on, that gives me certain, generalizes the circular motion. Now in this particular case, because I was moving clockwise instead of counterclockwise, I have to make all of my angles go backwards. So I'm going to multiply the omega t by -1 to make the circle run backwards. Okay, wow. So if we put all of this together then, we can say that our x of t has to equal 5t, that's the linear motion part, plus the radius of the circle, which is 1 inch, times the cosine of negative, whatever the omega is, v over r. The v is 5 meters per second, or 5 inches per second, divided by 1. So that would actually be 5t minus pi over 2. And in order for the robot to win the race or to finish the race, that position has to be equal to 60. And so now we have an equation we can solve. The Newton's method part is easy. It was the setting it up that was the tricky part.
I'm sorry.
Yeah.
Why was the starting angle?
Negative pi over 2? Because the red dot is starting on the ground, according to the problem.
Oh, yeah.
And so instead of starting right here at 0, it's starting negative pi over 2. Oh, yeah, so what's a good starting guess for the time? What's a good starting guess for the t0?
12.
Good. Why is it 12?
This thing is going to be
And also, the cosine is going to be really small compared to this 5t thing, right? Physically, pretend that the wheel is just staying in one spot, right? It's only moving back and forth a little bit. That being the case, then the red dot is basically going to cross the line when the robot tests, which is going to be the linear motion of 5t. So if I set 5t equals 60, then I get t equals 12 as a good starting guess. And then I can iterate from there. You just need the one derivative here, so x prime is equal to 5 minus 5 sine, actually plus 5 sine of negative 5t minus pi over 2, just like that. And that's not so funny.
And do the x0 minus f.
Yeah, but this will converge really quickly. I recommend just letting y1 equal this and using the trace and the dy dx to get your derivatives without actually plugging in. You know what I'm saying? So if I were to set up my table with xn, I'd have 12 for x equals 0, for n equals 0, and then I would use trace to get the value of f and dy dx to get the value of f prime. So no matter how complicated, it's not a hard solution. It gives you something. Better? You're not sure about the circular motion. All right. Let's take a couple minutes to nail that down because everybody needs to know how to do circular motion. You guys didn't do like endless amounts of Ferris wheels and stuff like that in tree?
There was one Ferris wheel problem, and it was the difference. On one test, I don't believe one person could even,
What
I don't think it was ever gone over yet. Maybe.
Alright. Okay. A Ferris wheel rotates at, oh, how quickly should a Ferris wheel go around? It should probably take about 30 seconds per rotation. It has a radius of 15 meters, which is actually huge. And if a passenger starts at the bottom, and rotates counterclockwise, find the location of the passenger as a function of time. Okay, go. Just pick one. Yeah. Where do you think?
I just, so I'm thinking how to pick the instruments and the real from coupler and design thing.
Yeah. I would try x equals 0 as a starting point. It's not great, but it'll get in there. Yeah, your starting location, if you have a graph, then you should be able to read the starting location off your graph as a good estimate.
How's the graphic first?
Yeah, you can graph it first. If you have a graph available to you. Now, here, you get sine x and then draw the line negative x plus 1/2. And you can see it's going to intersect somewhere a little bit bigger than 0. So I might try x equals a quarter or x equals half. That's a good estimate.
And for
Because when we put initial volume 12
Mhm.
and when we
We did that because physically, the wheels are attached to the robot, right? So if the robot's moving forward at 5 inches per second and it's got to go 60 inches, the robot's going to take 12 inches to get there. And the wheel travels along with it. So the wheel is going to, the red dot's going to cross the line somewhere close to 12 inches, to 12 seconds. You're not picturing this. So I've got my robot, right? And I've got the dot on the wheel. And the dot's going around as the robot goes across. Well, after 12 seconds, the robot is going to cross the finish line. And I don't know if the dot's going to be here, or if it will have already crossed the finish line, or something like that, right? It could be, but it's going to be close to t equals 12 seconds. So that's a good initial guess. Oh. Okay, so you should have found that the period is 30 seconds. Yep. And therefore, the omega is going to be 2 pi radians divided by the period, which is going to be pi over 15. That's actually the slightly trickiest part, and it's simply, it takes 2 pi radians to get all the way around the circle, and it takes 1 period to get all the way around the circle, and so your rate is 2 pi radians divided by 1 period. The radius is given, 15 meters, and we're starting at the bottom, so our initial angle is negative pi over 2. And therefore I can write that the position x of t is going to be radius times cosine of omega t plus b, comma, radius sine of omega t plus b. And that's it. I'm done. Yes.
So is that just like this and small test?
Yep. Differentials also. I think I'm going to need to put out a video with the differential stuff on it.
Theta is always omega times
Yes.
always.
Because we have a constant rate of rotation.
And the starting point should be bottom, so under 2 pi. That is counterclockwise.
Right. What's remarkable is we did all this in physics too. No, I didn't talk about that. We did this. Questions? Does this make more sense? Think of it as being very similar to finding the equation for y. For an equation for a line, you need what 2 pieces of information? Slope and point. To find the equation for a sinusoid, you need what 3 pieces of information? You need an amplitude, you need a rate, and you need a starting angle. And that's really kind of it. Okay, let me get started with differentials, and then I will finish up on video. Got about 15 minutes. Can do some things. I want to consider a curve y equals f of x. And we're going to draw ourselves a tangent line of x equals c. And we know already that the tangent line has the equation y equals f of c plus f prime of c times x minus c. And we can call this the local linearization And what we are guaranteed is that for x close to c, in other words, in the neighborhood of c, f of x will be approximately equal to the tangent line. In the video, I'll make that more precise with epsilons and deltas. We're just going to take this as approximately close to. Now what this means is that I can, two things, that I can use, first of all, the local linearization to estimate y values for f of x. And that's what we're going to be talking about today. I can also use the local linearization to estimate x values, and that's what Newton's method is. You say, how is that estimating x values? Because if I want to estimate x values for a particular y, then all I have to do is to create f of x minus y equals 0, and solve for the root there, and now I've got an x value for which f of x approximately equals 1. So Newton's method is all about using my tangent line, my local linearization, to find x values. That's it. Today we're going to find y values. So how are we going to do that? Well, there are a couple of ways that we can go about it. Let's get a problem up on the board. Let's estimate the square root of 251. Okay. Now I picked a value that's large enough so that hopefully none of you can do that in your head. Maybe you're one of those savant people that can do that in their head. I can't. Okay. What I'm going to do is I'm going to think of this in terms of a y value for a function. What function is this obviously a y value for? F of x equals what? What function am I trying to find? The square root of x, that's right. So I've got a function which is the square root of x. And I can now choose an x value that is close to 251 that I actually know the square root of. Does anybody know an integer that is close to 251 with a known square root? The integer is 256, and its square root is 16, right? So I'm going to choose c equals 256 because I happen to know that f of c is exactly 16. This is a known anchor point for me. And so I can now compute the tangent line y equals f of 256 plus f prime of 256 times x minus 256. And all I need for this is an f prime, which is easy enough. It's 1 over 2 root x. And f of 256 is 16. F prime of 256 is 1 over 2 times 16 times x minus 256. What does this mean? This means that this straight line right here, which is easy to compute, is going to be approximately equal to the square root of x, the original function, for x's that are close to 256. So that I can estimate the square root of 251 is approximately y of 251, which would be equal to 6 plus 1 over 32 times, now watch this quantity right here, 251 minus 256. I can rewrite that as negative 5, right? And so I get 16 minus 5 over 32. And a quick 4-function calculator can do the trick for me here. and I get 15.8438. How close is that to the actual retail square root? Actual square root is 15.8430. That's not bad. We're off by 8 parts out of 10,000. Now what I'd like to do is to take this concept, you guys are comfortable with tangent line estimation, right? Okay. I'd like to take this concept and I want to just relabel some stuff. So coming back up to here, what I'd like to do is to take this guy right here, and I want to rewrite x minus c as the quantity dx. And dx is going to represent the distance along the x-axis from x to c. And when I change by an amount dx in x, my tangent line is going to change by a corresponding amount dy, and dy is equal to y on the tangent line minus f of c and if you look at this equation right here, what it's really saying is that dy, which is y minus f of c, is equal to f prime times dx. Just by relabeling what we did here. Now, Leibniz would have loved this. He would have said, well, of course, because f prime of c is simply equal to dy over dx, and that's equal to c, right? See? But see, Newton's going to fuss at him. He's going to say, no, dy dx is not a quotient. It's the limit of a quotient, and that makes a huge difference. The limit of a quotient is not the quotient of limits when the denominator goes to 0. Okay? So Newton's going to have a conceptual problem with Leibniz. Leibniz is going to say, it doesn't matter. What I'm doing is I'm taking and I am expressing a change in y along the tangent line, as rate times a change in x. And I can solve all sorts of problems with it, Mr. Newton. What Leibniz is doing is he is using dy as an estimate for delta y. Now what is delta y? Delta y is going to be the actual change in the function. It's going to be f of x minus f of c. And you can see that delta y is not exactly the same quantity as dy, but it's close. And when x is close to c, that difference can be negligible. I can get it to be less than an epsilon for a particular delta y. Does that make sense to everybody? So if we were to come back and use this idea of differentials, we're going to call the dy and the dx the differential changes. The differential changes in x and y. Then we would solve the square root problem like this. We would say that f of x is equal to root x, and I have a dx of 251 minus 256 is negative 5, centered at c equals 256. And we would say, therefore, dy, the change in y that results from that, is equal to f prime of x times dx, or 1 over 2 root x times dx, or 1 over 2 root 256 times negative 5, which is negative 5 over 42. This is the approximate amount of change in the square root that results from a change in x of 5. And since the original y, which was root 256, was equal to 16, therefore my new y is equal to the original y plus dy excuse me, is approximately equal to the original y plus dy, which is equal to 16 plus negative 5 over 32, which is whatever it is. So notice that we're doing the exact same computations, but we're thinking about them in a little bit of a different way. And that is that we're thinking about them in terms of change. I'm changing x by a certain amount, and as a result, y changes by a certain amount, which is rate times change, gives me new change. What I'll do in the video is I'll talk about how we can use this in a practical way to compute errors in computations when we have measured data that has a certain amount of tolerance to it. So in particular, I might ask this question. If a circle has a measured radius of 10 plus or minus 0.2 centimeters, what is the error in its area? That's the kind of question that we'll answer with differentials to make it really kind of easy. Okay,